right. This is your office hours. What do you guys want to work on?
One of everything.
One of everything? There's a lot of stuff. What are some of the topics you guys are struggling with?
Can you do bearing and shear diagrams? Like a problem with that impossible.
There's no such thing as a bearing diagram.
Oh,
It's a bending
I think
diagram.
bending, my bad. Bending.
Big difference. Bearing diagram is compression tension, basically, but excluding the tension. It's just a compression diagram, and that's us.
Professor Tucker, how many topics are there?
Yeah, what falls in this?
Everything that fell between the last two homeworks.
Okay.
So these are going to include everything beam related. Everything and anything and everything beam related that we've covered so far.
So everything after exam two, basically.
Yes. Yep.
So basically, study one for 7.
Basically, yeah. Mm-hmm.
We didn't get our homework back.
Homework 8?
Yeah,
I have that. Thank you for reminding me. I did grade everyone's homeworks. Everyone saw their grades on Brightspace, I think.
For which one?
Homework 8.
Yeah, I didn't.
Most of you, unfortunately, got demolished this past homework.
76, let's go.
So I made sure to put extra problems on this homework.
Lowest homeworks get dropped.
Yeah, they do.
Okay. Please.
Oh, you cut it off the 60. Man, that's
All right. Share and moment diagrams. All right. But those are like the fun, easy topics. All right. Let's see. Let's put... Nope. I don't even want that. A pin and a roller here. 5 kips. And 10 kips. Let's make this 3 feet, 5 feet. Nope. Make this 4 feet, 5 feet, and then 2 feet. I'm going to give you guys 10 minutes to draw V of X and M of X. That's how long I think this problem should take you guys. Because it would take me about 2 minutes. Just kidding, I already did it in my head. I'm going to use this time to eat. I didn't eat. Entire motor diagram. And as for the shear force, I would need to solve for it, but.
it starts rolling.
And, cause
Some
of the
right.
areas go left to right. Some of the areas. Some of the areas. Did you not take notes? No. Cause I'm just visualize it. Cause this, no, I'm asking you guys to try.
It's
Come
like
on.
I'm absorbing all of the information.
You know what, you're giving me an idea. I'm gonna have people come up to the board to solve the problem.
Yo, do it on a good.
Okay, wait. Today is a good day. Every day is a good day to be alive. Yes, sir.
So, is it used to be your
I'd still work with them all last year.
You're making an assumption of reaction.
It's just
Where are
nice
you
to know
taking
that I
your
don't
mind?
get-
So you've got -5.
Unless I did it before.
The thing is, even though the source is -5 kips going downwards, it's causing a positive rotation.
Also, then it would be.
Yeah,
Oh, okay, okay.
don't, just add the negative and positives after you write all of the equations, because then, you can account for how they're rotating.
Okay, so I'm not gonna assume that before.
Yeah, don't look at the
Then I'll-
directions, yeah.
Okay.
Because technically, if you wanted to do it, then the perpendicular distance is technically -4, so -5 times -4 would give you +20.
Okay.
Does that make sense?
Right.
So if you wanted to do it that way, my recommendation is just look at the rotation.
Okay.
Yeah. So, you wanna solve it?
No. But I can show you.
Okay.
So we have slides. This is where I saw the line. So we have the distance right?
Moment at this point is equal to what? What is the bending moment at that, at the reaction? How would you calculate that? Don't try and be so theoretical, just work the numbers out. How many important points do you see on this diagram? 1, 2, 3, 4. Calculate the moment here, calculate the moment there, calculate the moment there by summing everything left and right.
All right. Hopefully everyone has an answer. Olivia, did you figure out what the moment diagram? No? Let me see what you have. I want to know. All right. So, did you get an answer?
We'll see what's like that.
I want to see it now. I want to see it now.
I'll be sure.
What'd you get for the moment at least? What value?
Because I think what messed me up is the fact that the forces are on the outside, so I
Yeah.
feel like I did it wrong. And I also get confused when it's attached to the wall. That's when I mess up.
You know, this might look a little weird, but like one of the important things that it can represent are, for example, reaction forces to a truss system with a roof overhang on either side. So that's a nice little thing. But
Unless there's more factors working.
let me ask this. What did you guys get for the reactions? What are the reactions?
5 and 10. 5 over AY and 10 over
5 kip, 10 kip. Did everyone get that? No? That's a problem. All right. How many of you took a moment about here? You took a moment there? Wrong.
Where did you point?
Don't take right here. If you took a moment there, immediately wrong. Always take a moment about the reaction forces. Preferably take it always about the pin. All right? So, we can call this A, B, C, and D. You take a moment about what point? A, B, C, or D? What are 2 points you can take moments about? B and C. If you took a moment about A or D, immediately wrong. Go back to statics. I'm kidding. Well, you're past statics, so don't go back. All right? Has to equal 0. And so we have a 5 kip force with a perpendicular distance of 4 feet. And is this causing a positive or negative rotation about B? Positive. Even though it's a downward force, it's causing a positive rotation. Next, we have CY times 5 feet. And is this causing a positive or negative rotation about point B? Positive. And then lastly, 10 kips times 5 plus 2 is 7 feet. Positive or negative rotation? Negative. So you solve for this. What do you get for CY? 10? 10 kips. And so just by deduction, BY has to be 5 kips, just from sum of the forces in Y. Next, follow tip to tail. All right, 5 kips on the very left-hand side. We start at the very left-hand side of the beam. You gotta go down 5 kips. Is there anything between A and B to cause a increase or decrease linearly? No. So it's just a straight line across and then jumps up. And this is negative shear with a value of 5 kips. From here, is there anything between B and C to cause a linear change? No. It means your shear between BC and 0. From here, C, you go up 10 kips. And is there anything between C and D to cause any linear variation? No. Straight line across, drop it down, you got 10 kips. Everyone got the shear force diagram, hopefully. Or if you didn't, you guys understand how we get it? Good. All right. Now, how many shapes can we break this up into? Or how many critical points are there? There's going to be critical point 1, critical point 2, and critical point 3. We could calculate M1 using the equation, what? What is the bending moment equal to? Area of the shear force diagram, right? So M1 is going to equal negative 5 kips because it's negative shear. And the length that it spans is 4 feet, which gives us negative 20 kip feet. So what we need to do is draw now the bending moment diagram up to that first point. How is that going to look? Straight line, 0, linear, quadratic? Nope. Linear. When I mean straight line, I mean like it's just horizontal like that. So you probably meant linear, right? Yeah. And that puts us at negative 20 kip feet. Now, is there any shear between BC? No. So M2, if we call this point 1, point 2, M2 is just going to equal negative 20 kip feet. And then what's the area between 1 and 2? 0. So the bending moment is negative 20 kip feet. How is this going to look? 0, linear, straight line, quadratic, straight horizontal line. And then lastly, when you calculate M3, you should get negative 20 plus 10 times 2. And if you did everything correctly, you should close out to 0. And bada boom. That's our bending moment diagram. Now, fun little hint, fun little note. Whenever we have a portion of the beam that is subjected to a straight line shear with a straight line bending moment with 0 shear, the beam is generally subjected to what we call pure bending. There's no shear forces, It's undergoing pure bending, we call it. There's no translation at all. Anybody want to take a guess at how this beam is going to deform? What do you guys think? What will? The whole thing will go up? Or between B and C, right? That'll shoot up and then everything else will what? It'll just stay where it is? Yeah. So this beam will actually deform kind of like this. I'm going to draw it in light blue. Something like that. It's actually a horrible sketch. Just like that. Where there's going to be some vertical translation here, some vertical translation here, some vertical translation here. Make sense? Good. All right. Now, assuming that this is A992 steel, give me the minimum S shape. Check bending and shear. And assume a factor of safety of, I don't know, Emily, give me a factor of safety. 2. All right. I'll give you guys 10 minutes to do this problem. You guys can tell me what the minimum factor of safety, well, not the minimum factor of safety, but yeah. And remember the shape I said. Don't be looking at the W-shaped table or the steel angle table. How was everyone's weekend, by the way? It was good. I just played games with my brother most of the weekend and hung out with my girlfriend. And then graded your homeworks.
25?
What?
25?
Yeah. Yeah, I'm getting up there in age. Could be walking with a cane soon. Or looking worse. Breaking my rib like a particular professor in this department. Shots fired. Yeah. I should just make that an exam question. To determine the deflection of the ladder rung before Albert fell off of it. That would be so mean, though. What?
What was the definition?
If Al had an elastic modulus. 0 stiffness. It took me a while. He corrected me when he showed up one day. I was like, "Hey, Professor Dawson." He was like, "Call me out." He's like, "We're coworkers now." Because I still call everyone Professor. I don't call Professor Francelon anymore. I call him Wesley. Mike, I now call Mike because he told me stop calling me Professor Simon. It's a big change. And you know, when you said Professor Tucker, that threw me the hell off. Because
You do this.
not used to it.
Oh, be careful, bro. There's a lot of stress on your knee. You don't wanna.
No. Yeah.
Do we have MX? Would that be the negative 20?
You should be able to decipher that. And also, just so you guys know, I know we didn't do any examples with it. S shapes for shear, average web shear approach also. So you don't need to use the VQ over IB equation.
check shear? What? Yeah, when you design a beam, you gotta check both. Because unlike bending failures, shear failures are instantaneous usually and very scary. Mhm. What? Is the difference between seeing cracking in the middle of the beam versus the ceiling falling through? Which one would you rather see? Would you rather see it and be like, all right, I need to get out of here, or just the ceiling fall on you and kill you? You'd rather have a chance.
I don't think you're gonna have much of a chance on the way.
I don't know. Have you seen the bridge outside?
Yeah, did you hear about the Smith Point Bridge?
Which one?
The Smith Point one? One of the columns starting to deform, like it's not supporting as much as it should, so then they have to limit the size of the hinge track. But you know what's funny is, I promise you, it has some construction that they were doing last time I was over there, it looked like they were adding some, like a state, like, I saw them drive, through that shape, so they're building something big, they're building some type of, today's not like violator thing, about the hair, everything else, which is pretty cool. But I'm telling you, all that equipment between that and then like, I think that was it. Then I saw them using barges to transport some of it, so I think they had an idea about it way before the commission.
Yeah, most times departments, some engineers will generally figure it out. It's the main issue from budgeting. You know,
That's what it looks like you just don't have,
budget.
doesn't really want to pay for it, because, you can see it, like, yeah, it's always kind of been there, so I remember as a kid, but now it's just not really.
That happened on one of the projects I was working on. We did inspection, the contractor did half-ass job on the whole project.
Because it got cheaper and cheaper and cheaper, right?
Yeah, and then the client just ran out of money in this, so they canceled the project, and now the tunnel's falling in.
So, that's the way we try to do it, the standards, the same project or not?
The turbine, yeah, I had to do inspection work for it over the summer, snowstorm.
So it's caving in, so.
Yeah, and the shotcrete, because it's such poor quality, is falling off in like chunks the size of you and I.
So, you inspect, so you work inside of that.
Yeah, I just walk around it for a bit, maybe for like 4 or 5 hours, looking at every last nook and cranny of it, and every crack that develops, making sure that nothing else falls through, and just trying to figure out when. Basically, they wanted us to measure how bad cracking was, and we were like, it's not the cracks that you gotta worry about. You gotta rip this entire thing off.
So is it, is other, so, right, so, I mean, what do they do, like underpin it, like reverse underpin it, you know what I'm saying, like, to replace it, like, go without that, or just.
No,
close it down?
it's in relatively capable rock, but granted, you can't leave it unsupported for a long duration. But they'll probably need to demo certain parts of the shotcrete lining and then just respray it as it goes. Yeah, the forces will just get diverted to other parts of the lining.
Okay,
Yeah.
so you support it as like if you're like removing like a bearing wall in a house,
Mhm.
okay, that makes.
Yeah.
My bad, I was just interested in
All right, who here's got a W shape?
that. Engineers appreciate.
What? Yes, S shape. Thanks for the correction. First mistake of the semester. Nobody's got an S shape yet? Did you get an S shape? At least for bending. You did? Which shape? You don't know if it's right? All right. So, first of all, what is the entire point of drawing these diagrams? Is to get the internal forces, right? So, what is M max and V max? What are our design forces? These are the forces we use for design. What are they?
ZMX 20 and the other ones
M max is going to be the 20 kip feet, and then the maximum shear is 10 kips. All right. Are these the design forces, though? No. The design forces account for a factor of safety of what? 2. So MDES is equal to 40 kip feet. And then VDES is equal to 20 kips. From here, first step with all of the beams that I've told you is check bending first. This is just sigma is equal to my over I, which we can simplify to just be m over s. We can rewrite this to then just be the bending moment divided by the stress, which is just 40 kip feet times 12 inches per foot, because we got to keep the units consistent, divided by the yield strength of the steel, which for A992 steel is 50 KSI. And from this, what did we get for the required section modulus? 11.6? 9.6. All right, now I don't have the table with me. I forgot mine at home, but what's a W shape that worked for you guys?
W or
S, sorry. I keep saying W shape because I'm so used to coming up with the W shape problems.
Would be S8 by 18.4.
S18 by what?
S8 by 18.4.
Is that the lightest shape? It is? All right. What was the section modulus for it? Yep, that works. All right, from here, check shear. We use the average web shear approach whenever we are dealing with beams with a flange or 2 flanges in a web, because we determined last lecture that by using average web shear approach, we can approximate it as the maximum shear stress by ignoring the flange contribution. So we just use V over A web. The shear design shear force was 20 kips divided by the area of the web. I'm actually going to erase this because we technically, this has to be less than, what was, what's our design, what's our capacity for shear? Remember for steel, how we approximate the shear strength of the steel? Yeah, what is it?
Is it 60% of the yield?
Yes, it's roughly 60% of sigma y. So for 50 KSI multiplied by 0.6, that's going to be 30 KSI. All right? This only applies to steel, by the way. So if for some reason I don't give you guys a steel shape, I will give you guys a property that has a shear strength specified on it, all right? Otherwise, if it's steel, use 60% of the yield strength. All right, so now we got to check it. What is the area of the web going to equal? How do you get that? Are you taking the area of the entire shape? Yep. So we could find the depth of the web. We call it dV. You can also say it's the depth of the web if you wanted to be more specific to what it is exactly. And this is just what? It's the D minus 2TF that we've been dealing with, right? The depth of the entire beam minus the thickness of the flanges. So, what is the depth of the beam? It's roughly 8 inches, what's the exact value? It's exactly 8 inches? Oh, wow. Minus 2 times thickness of the flange. What is 0.425? All right. Now somebody tell me what that value is. All right, good. Now from here, the area of the web is just going to be the depth of the web, yikes, times the thickness of the web. Depth of the web is 7.15 inches. And then what's the thickness of the web?
271.
Do this multiplication. Tell me what you guys get. From here, just plug in. The shear force was, design shear force was 20 kips. Divide this by the area of the web, 1.93 inches squared. And what do we end up getting? Obviously, it's smaller than 30, so it's clear we're good. But what do we get for the value? You got it?
Yeah.
All right.
10.39 KSI.
And because that's less than 30 KSI, we're good. So our shape works. Make sense? Awesome. So this was an example. All right. I'm going to give you guys something a little bit differently now. Yikes. Let's say that this is a length of about 15 feet. Nope. 5 feet. And that this is a, I don't know, pick a shape, Michael, any shape.
W16 by 40.
Ironically, that's the steel shape that Mike has in his classroom, if you guys ever saw that. All right. Assuming that this is A36 steel, determine the max load W needed for the beam to fail. So now you're reverse engineering. What is the required load for this beam to fail? I'll give you guys 10 minutes. And of course, check bending and shear.
remember, for simple loads like this, we have tape. So if you're trying to draw out the shear and moment diagram, sometimes simple load cases like this can just be found in the tape. Does that make sense? there a fixed end on this?
So, oh,
Yeah, it's a simple pin and roller. You take a look at the reactions. So something like this generally means that there's a moment stop. Alright, it means it's fixed in some time. What you really want to look at is normally very first one. Yep. Just understand what the reactions are representing, alright?
yeah.
Yeah.
Well, where are you getting these values though? No. I'm asking you what the maximum value for W is. 40 would just get added on. But you can ignore the self-weight on the beam, guys. Alright? Nope. The entire problem is asking you what is W, which means you don't know the bending moment, you don't know the shear force. You only know how the diagram roughly looks, which is this. Alright? Why isn't it making sense? Figure it out? Something makes sense.
Yeah, ignore self-weight.
That's the steel, the NDS packet. You didn't get one of those? Are you sure? Because we've been doing, because we've been doing beam problems for like weeks, and I thought I gave everyone one. No? Alright, got it.
W squared over 8 and multiply your size by 8.
Show me where your actual paper is. I don't know how that's. Which makes sense. No, it makes sense.
Yeah, L squared stays together. When you separate the W
Yeah.
We're still trying to find W. So that's what I found that.
Yeah. This is an L.
No, after that.
Please. 518 as max.
Nope.
This ain't the same as M max. M max is going to be dependent on that. So you need to find the capacity of the beam first. Yes. Nope.
Solve it mathematically.
This really could take more.
It's your exam.
Can we see it?
No. Yeah, you can on Thursday. All right. I'll give you guys a 5-minute break. 7. Let's come back at like 7. It says on the computer 7:12. So let's come back at 7:17. Computer 7:20 on the clock. And then I'll go over it for you guys. But does anyone have an idea on what they're supposed to do for the problem? Yeah? Explain it to me.
I think so.
You think?
First you gotta find M max, right?
Yes. And how do you find M max?
S times, I already forgot what it was called. The stress for the steel.
Mm-hmm. Times the section modulus, right?
Yeah.
We can divide them or?
Multiply them because stress is equal to M over S, which then you rewrite as M is equal to sigma times S.
Oh, I divide.
Yeah. With that problem, you don't know what the bending moment is, so it's kind of like going backwards on our problems.
You multiply with SX by what? RX?
The stress. No, Rx is the radius of gyration, which that only comes into play for buckling. So don't even look at Rx. The only two things that you should be worried about are Sx and Ix, because they're related. Before anyone asks, I already had Professor Simon look over it, and he told me the first revision of this was too complicated, so I lowered it. So it should be nice and easy. He said it was a fair exam. So please don't be emailing him. It's too hard. I've already received twice complaints.
But this problem is definitely going on the test too. Yeah, this is probably too easy for the test, right?
This problem?
Yeah.
Did you solve for it?
Yeah.
Clearly not easy enough.
It was, yeah. I got 492 pounds.
Per foot?
Yeah.
How'd you do it?
Well, I'm going from looking like they were
492 pounds. I'm interested. You know what? Better yet, I would like it if you would write it on the board for us.
Well, I didn't do it.
How'd you come up with the numbers?
It was genius. It's just like a hidden talent.
Mm-hmm.
I can look at things, think of it, get it. It's also cool.
You just you just plugged and chugged until you solved it.
100%.
492 iterations it took.
What's the legitimate answer? Do you have anything?
No. I don't even have, look, when I make your exams, I don't even know the solutions. Like, I literally have no clue how difficult the exam is. I just showed it to Simon and he was like, it looks fair. The questions could be entirely messed up. Like, that's what happened the first exam.
Wait, so how do you make
That's
them?
comforting.
You just buy your house and just make the exam?
Yeah, I've just come to learn, just take questions from random textbooks. They're easier than drawn up of problems.
So in accurate, you have to do your own exam and solve it and hope that you have the answer keys right.
Mm-hmm.
But what if your answer keys wrong?
That's why I make sure it's right. With this stuff, I know what I'm doing usually. Like, I make minor calculator errors, and if, you know, I made a mistake or something like that, I could at least go back in afterwards and update everyone's grade.
What is VX on the table?
Oh, that's the function. So, you remember how we would cut sections, and then you would get shear as a function of x? That's what it's representing. It just describes the shear at any given point.
Are we getting
Flashcards?
Yeah.
I gotta give those out. Thanks for reminding me. I don't think I brought them. I'll be right back. I'm gonna have to go steal some flashcards. I forgot to bring mine.
Give me 2 extra bonus points or more. I get it. Just cause.
Well, I think it's like a 7 for shears. Like, that's why we're just.
Oh, you did math. What the, oh, 'cause the lowest one
You
gets
get
dropped.
attention from one.
So-
Yeah, that's, I have to get shears, the 7 both tension and shear. There's only 2 left.
I would just use
Yeah.
the shear, no?
This and the final. The final is technically not the final, it's just a quiz.
It's just another test.
Yeah.
But also, you don't know what the curve is yet either.
I can't depend on it because.
No.
Does he only curve exam?
I think he curves the ads up in there.
36.
Oh, the average, okay.
Okay, that's what I did.
Oh, that's not even.
160.
Why?
I
down to max. You don't
And
need
he's
to
from, I don't know where.
I mean, it's well easy to me, but
To separate the.
I don't know.
And then algebra for me was such a
Alright, look, you just
Algebra
take
two.
W
No, I'm working on
five.
I got a C plus. in that.
Algebra
And then I
one
was
is like,
just like,
the easiest place to.
I was worried.
About 1500.
I thought I was gonna have to let you guys use an entire sheet of paper. Fortunately, I found flashcards.
And you divide by 25.
Are we using this one side?
I'll do a coin flip over and out then for a sheet of paper.
Nah.
Yeah, when I did algebra, because I
Why don't you
had
do
been
like
in high school for
Okay, I just did it.
7 years.
That's fair,
but-
yeah.
All right.
Are we using one side or both sides?
There's not many equations, so one side. Yeah, one side for this exam. Fine, I'll be nice. Both sides. All right. If it makes you guys feel more comfortable, you can use both sides. All right.
One fuzzy now.
What? You feel warm and fuzzy now?
Why I didn't both sides.
What?
I can't even think of why I didn't both sides though, because there's not that much.
Yeah, the only two equations you guys learned was.
Are we using this one?
Yeah, you can use those. Just as long as you don't have like anything like suspicious written on it, like you can write whatever you want on it. As long as you're not like, like if it's stuff to help you guys like understand how the tables work, fine. Just as long as you're not like for example, like putting full-fledged example problems or being like answer to problem 2 is is A or something like that, you know? All right. So, Joseph, since you said you solved it. I'm kidding. All right. So, first part of this problem, we don't know what W is, all right? Which means that M max is unknown and V max is unknown. But what do we do know? We know that M max and V max are dependent on W. So, when we do our comparison checks, we usually determine what? We determine the minimum size W shape that we need for the given bending moments, right? This time, we need to figure out what the bending moment is for a given capacity. How do we determine the capacity of a beam? Well, first of all, let's check bending. What is our bending stress equation? If you guys can't tell me, this is a problem. Bending stress equation.
M equals sigma over S.
Well, sigma is equal to m over s, but what's our unknown here? M, because we know the stress and the section modulus, right? So we rewrite this to say stress times the section modulus. The stress of A36 steel is 36 KSI, and then what's the section modulus of a W16 by 40?
64.7.
All right, and that gives us a bending moment of what?
2,300.
And these are going to be in units of kip inches. We can convert this to kip feet by doing what? Divided by 12. So, taking 2,329.2 divided by 12 inches per foot. What do we get for kip feet?
194.
194 exactly?
0.1.
0.1 kip feet. And this is fortunately our M max. Now, what does M max also equal to? Let's say we did have W. What equation would we use? Yep. We know that M max is also equal to WL squared over 8. Which, when we plug in everything, we have W. L is going to just equal what? 5 feet. Which, what does that give us? As no one proceeds to tell me. 5 squared divided by 8. That's 25 over 8. What is that?
3.125.
3.125 W. Or you could just say 3.125 feet squared W. You set the two equal to each other, and what you should get is 194.1 kip feet divided by 3.125 feet squared, which gives us a distributed load equal to what? 62.1 kips per foot. Is that what everyone gets? Yeah?
62.2. I did it a little.
That seems very large. But I guess it's a very short span. So let me just double check. 36 times 64.7 divided by 12 divided by 5 squared over 8. Yeah, 62.112 kips per foot. So roughly 62,000 pounds per foot. All right. That means my suspicion is it's probably going to fail in shear more than likely. So now let's check shear. Tau is equal to V over A web, right? Area of the web is just equal to the depth of the web times the thickness of the web, which we know that the depth of the web is equal to what? What is it? 16 inches. Is it just 16 inches? Of the web.
Oh, hold on. You gotta subtract the 2 times.
Subtract the flanges. The total depth is 16 inches. Depth of the web is going to be 16 inches minus 2 times, what is the thickness of the flange?
0.505.
So that's roughly what? 14 point...
99.
Yeah. Is it? What is it? 14.9 inches? Or 99?
I got 99.
16 minus 2 times... It's probably, yeah, you're right. 14.99. All right. So we have a shear force divided by 14.99 inches. And then what's the thickness of the web?
305.
I'm actually just going to leave that there. 0.305.
Yeah.
Which gives us an area of 4.57 inches squared. All right. What's our unknown in this equation? What are we trying to solve for here? Not quite. The shear force. Well, yeah, because we know what the shear stress is. What is tau for steel usually? If we know the capacity, for the capacity. 60% this yield strength. So for A36 steel is going to be 21 KSI. Which means that our shear force or shear capacity is just going to be tau times A web So 21 KSI times the 4.572 inches squared, which gives us 96.01 kips. Yeah,
How did you find tail again?
it's on the table. It's just the capacity of your beam. All right. Any questions so far? Everyone following along? All right. From here, we have A web, we have the shear stress, we calculated V, but what is V also equal to in terms of the load? Does WL over 2 ring a bell? Look at figure 1 in your packets. You guys see that? So we can now rewrite this to just be 2V over L. So 2 times 96.01 kips divided by 5 feet, which gives us 38.4 kips per foot. So W for bending was 62.1 kip per foot, and W for shear was equal to 38.4 kip per foot. What's the max distributed load we can apply? 38.4 or 62.1? What do you guys think? Shear. Can't go any higher than 38.4. If you do, you'll fail. Yep. So this is one of those instances where if I had just given you the distributed load and you did the checks and you computed what required bending capacity you would need, right, and found the section that way, your shear would have actually failed, which means you would have had to continually kept choosing different shapes to make sure that the shear worked. Make sense? So that means this is the answer. Let's do another example. What do you guys want to do next? Yeah.
Can you do one of the examples with the two materials where you transform them?
Yep. Composite. Say I've got a material here. And a material here. And let's say that this is, I don't know, I don't have my packet. I'm going to borrow somebody's. Can I borrow your material packet? Thanks. So I'll choose 2 different materials on here. I don't want to make them too weird. So we'll say that this is copper and that this is yellow brass. Annealed copper. And what I want for you guys to do is determine the neutral axis and the second moment area of inertia. I didn't touch anything.
Of the, cable is loose in that computer.
It is?
It's the same for, the, press machine, apps,
You guys should be able to do this in 10 minutes. So by that logic, you should have the entire exam done within 40 minutes. We can only hope, right?
4 questions?
Plus true false, as always. Yeah.
Or written, like, written problems and then written false.
Yeah. That's the one thing Mike hates is the true false questions, but I like them, so. Because they make you actually think of what this stuff is. And by the way, you can do these problems with more than just these materials. It's just I don't plan on doing that, I don't think.
Like 30 materials?
Yeah, you could do them for like 10 materials. It's all the same process. It's just like, remember when we did it for axial loads, how you had like 3 or 4 different components? It's just like, you would just add more material to the columns and then just find the modular ratio with respect to one base material. Does that make sense?
What to do? I just wonder how it's gonna come. Do you know it? No. I told it to you like 3 months ago.
My grandma used to work like 5 years ago, and then grade school, so we broke. Just like 45 year old man, never shaved, just like long enough years in the woods, hair too. Ketchup stuff in there.
Yes.
I have a quick question.
Sure. What is your question?
I have to do with for my IFX.
What?
Has to do with like IFX.
Okay.
So you know how like you have to multiply n times like the 4 inches?
Mm-hmm.
Would you for the IFX for like the bottom portion, so like yellow brass, would you also multiply the 2 by
For everything. That entire table should be for a transformed section of everything in one material. So for example, if this yellow brass, how did you transform it? Annealed copper to yellow brass? Or yellow brass to annealed copper?
I don't know how to like word it, but I did the larger one, so the 17,000 PSI, which is the annealed copper. That one I multiplied
So which
by
one's on the top? When you calculated N, which value was on the top?
annealed copper.
Annealed copper. That means you're converting annealed copper to yellow brass. Which means that the annealed copper should get wider.
Yeah, I multiplied that by n.
Yeah. So because of that, you use the annealed copper's updated geometry. So now the annealed copper, whatever dimensions you use, turn into yellow brass.
So when I find I of x for the yellow brass, I multiply by n also, just for the I of x.
Mm, For the annealed copper
So
part,
it's just gonna be 4 times 2 cubed divided by 12 for the brass I of x.
4 times 2 cubed. Let me see.
Yeah, no, I'm just trying to figure it out.
Joe, what? Slacker. What is this?
I thought you did this.
Oh. No, I printed my own. Oh, okay. Let me see this. What the hell? I'm kidding. Watch this much. 24.11. Where is that coming from?
That's for the, linear column.
4.52
Because I multiplied.
times 4 cubed divided by. Okay, yeah. Yeah, that's right.
So for, my question was just for like 2.67. This was just 4 times 2 cubed by 2.
Exactly, because everything is all with respect now to the yellow grass. You don't need to touch anything yellow grass related.
Okay.
All right?
Alright, yeah, that's all I have.
Mm-hmm.
Thank you.
Did you figure it out, by the way?
No. I'm looking through other things that I.
Sorry, I'm looking at this thing from my other class.
No, for the.
I used to do that. Professor Simon used to get so pissed off at me. When I was in, well, it used to be called site planning, but I don't think they have that anymore. I would do, I would do statics homework in his class, and he used to get so pissed off. Yeah, what do they call it now? Print reading.
It's the blueprint comes?
Yeah, but they don't call it.
Yes, the
What do you guys do in print reading?
blueprints.
Just reading and interpreting blueprints, shop drawings.
Yeah, super simple.
It's like textbook.
Yeah, I should show you some of the shop drawings I see. Have you guys had to look at rebar shop drawings at all for structural applications?
We looked at structural drawings, so like this is.
Yeah, but like I'm talking about like concrete shop drawings for like reinforcement. Those things are a wreck.
We looked at foundations. Like, it's pretty-
Yeah, I should show you guys some of the shop drawings I work on. Those, I don't think you've seen them at all. They're just, it's just somebody threw up colors all over it and lines. What? Let me pull it up. It might take a few minutes, and my computer might make a weird noise because apparently one of the fan bearings is like out. So if you hear a rapid fan accelerating, that's because I need to get my IT department to look at my computer.
Do we give you that computer?
Yep. Yeah, they need to give you your own personal computer because like it's the only way to keep things safe in a secured area. Because a lot of the projects that I'm working on, I mean, like they're state and government projects, so because of that, you can't just really like have it saved onto your personal computer because, God forbid, like, you know, for example, one of the projects I'm working on right now is literally like a risk category 4, it's called, which is basically like, in the event that it crashes, it's going to cause a huge economic disaster for the country.
So you get a background check then?
Yeah, I had to get background checked for it. Mm-hmm. Had to get drug tested too and everything.
Really?
Yeah. Okay, it's still frozen. Are you guys all done with it, or you guys still need a few minutes?
I'm trying to find the intro access.
How did you find IX?
Oh wait, I mean, do we have to find the design force? That's what I meant to say.
There's no force I gave you. I was just gonna go over the second moment area of inertia, give you guys a moment afterwards.
Alright, never mind.
You guys wanna do that then? All right. Did you guys find a value for IX at least, or get close to? All right. So, first step, find N. What is N gonna be? Depends what you transform the material to. Typically, transform the less stiff material to a more stiff material. No, more stiff to a less stiff material. What's the stiffer material in this case?
Would be the copper, right?
Copper, exactly. Which is more stiff.
Your screen's frozen.
Is it? Oh, it's not frozen on the right-hand side.
Thought I unfroze it.
There we go. More stiff, divided by yellow brass, which is less stiff. And this is just going to be, what is it, 17 over 15?
Yeah.
And then what's that equal to in decimal?
I got 1.13.
Give or take. All right. Now, what we next want to do, I personally just like to draw a transformed section just so that way we can kind of visualize what exactly is going on. So, what we are doing is now transforming this copper to an equivalent yellow brass dimension. So the dimensions of the yellow brass are 2 inches and 4 inches. The height of the copper remains the same, but the width of the copper now becomes 4 inches times 1.13, which gave us what? 4.52?
Yeah, 4.52.
And now our entire thing is in yellow brass, which means our IX value is going to be in terms of yellow brass. So I should have really said second moment area of inertia of this material, but it's whatever. On an exam, I will specify it if I give you guys this type of problem. Or if I ask you guys calculate stress, I will tell you what the second moment area of inertia is with respect to what material, so you know how to proceed, okay? Not that it's just second moment area of inertia and then you're just left to guess on what the hell it means. All right, so from here, make your tables. You're gonna have component, area, y bar, I'm gonna call it y bar I, and then A, y bar I. We're gonna have top and bottom, I'll call it. Area of the top, 4 times 4.52. That is gonna give us 18.08. And then for the bottom is 8. Who here did it transforming it the other way? Transforming the yellow brass to annealed copper. Nobody else did it that way? Because either way, as long the IXs will be identical. We're not identical, but you'll be able to back calculate it. So, add the areas together, you get 26.08. Y bar of the yellow brass is just going to be 2 plus 4 is 6 divided by 2 is 3. Nope, I'm losing my mind. It's 4. 2 plus 4 over 2 is 4. Sorry. First mistake of the semester. And then the height here is 1 inch. This becomes 18.08 times 4, which gives us 72.32, 8, 80.32. Our Y bar total, I get as 3.08 inches. So that kind of makes sense to me. Like, I mean, the elastic moduli are relatively the same, so there shouldn't be too much of a drastic shift in the location of the neutral axis. But it is definitely slightly higher just because this material up at the top is slightly stiffer. From here, I just like to separate these values. Now calculate your dy. dy is just going to be the absolute value of your y bar minus your y bar I. meaning just take the magnitude. Don't worry about if it's negative or positive, because once you throw it into this a dy squared here, the negative's just going to cancel anyways. So 3.08, there we go. 4 minus 3.08, I get 0.92, and then 2.08, and then 18.08 times 0.92 squared, I get 15.30, and then 8 times 2.08 squared, I get 34.61. Add those together, and we get 49.91, and that's going to be in units of inches to the fourth. Everyone got that so far, right? Awesome. For Ix now, use bh cubed over 12 of the transformed section. So for the top, it's going to be the 4.52 times 4 cubed divided by 12. You should get 24.11. And then for the bottom is going to be 4 times 2 cubed divided by 12, 2.67, 26.78 inches to the fourth, which means your Ix for yellow brass, I'm just going to call it YB, is just going to be the sum of the two of the Ix plus 80y squared, which gives you 76.69 inches to the fourth. Now, what if I asked you guys explicitly Ix for the copper, and you accidentally did all of this transformation calculations for the yellow brass? Easy fix. Divide it by n, because what that does is it transforms all of your yellow brass to equivalent copper. So it's just going to be the 76.69 inches to the fourth divided by 1.13, which then gives you 67.87 inches to the fourth. Make sense? Great. Now, just really quick, M is equal to 10 kip feet. Find the stress in the brass. I'm going to replace this with BR. And find the stress in the copper. I'll give you guys a few minutes to do that. In the meantime, let me pull up one of my very fun and amazing projects that I totally love working on because I'm an engineer. Wait, this one took me days to review. Yikes. Yes. Here. Oh, did everyone finish writing it down, by the way? Yeah, all right. I am just unplugging some stuff just because I want to pull this in real quick. Then need to unplug this, I don't think. Let me know when you guys can see my screen. Oh yeah, this is stuff I work on at work. That's a reinforcement shop drawing for a base slab. Just a small part of the project. Yeah, you have to count every last piece of rebar, make sure every piece of rebar is correct in there. Just points of deduction, you know. You look at the drawing plans, you make sure that the locations of all of the reinforcement are correct. So like, for example, these are all like openings around like stairway openings. This is an elevator shaft right here. This is a ventilation shaft, I believe, or staircase, I forget what exactly it is. But like, you've got a ton of the reinforcements. This over here in the hatching, this is actually a slurry wall. So they actually constructed this entire thing, and then they excavated this entire circular area. And then this slab here is just one of like 4 levels of slab. Yep.
What is this supposed to be?
This is a vertical shaft, so here, let me... That's just one of those many slabs for the North Island, which is... No, that's South Island. That's the tri-cell. But it's basically something like, yeah, this is it. This is the vertical shaft here. So that reinforcement shop drawing that I was showing you guys, it's just one of the slabs that's going to get constructed. Yep. You guys never saw a reinforcement shop drawing or anything like that before? Yeah. God bless you guys. Yeah, it's fun. Like, I mean, you guys probably saw what? Like, some type of, like, steel drawings, and what do you guys have to do in that class exactly? Like, do you guys have to, like, count and make sure that sizes are the same, or you get...
Understanding and reading drawings, basically.
Where you find this, and
It's like pretty
intro little drawings, and you have to figure it out, do notes, sometimes find dimensions, and last, what size beam is used for this trellis, and what find the real.
So are you guys usually given, like, one set of drawings by, like, a contractor and then another set of building
You
plans?
have like a textbook that has like multiple drawing plans.
Okay. Yeah, just because, like, a lot of times, like, contractors will submit stuff that's supposed to represent the drawings, and then when you're reviewing the shop drawings, you're just supposed to make sure, like, that the contractor is doing stuff that makes sense. And then, like, you guys ever have to question anything, like, on the shop drawing and be like, what the heck is this that you're doing?
How are they like official, unofficial?
So they're real projects that came up, and these are just the shop drawings that were put into the textbook, including the textbook for us to work on.
Okay. That's cool. Guys figure out the stresses? I know I was talking a little bit about it, but you found it?
Yeah, I just don't know if I used like one.
Okay. No worries. So for the yellow brass, the Y value is just going to be the Y bar, because your neutral axis is roughly here, which means that this is going to be your Y for the brass, and then this is gonna be your Y for the copper. So this is just Y bar, and then this is just 6 inches minus Y bar. So 10 kip feet times 12 inches per foot divided by I, X for the brass. We could use 76.69 inches to the fourth. And we get 1.56 KSI. Oh, wait. I forgot the Y, the most important part, yes. For the yellow brass is the Y bar, so 3.08 inches. That gives us a stress of around 4.82 KSI. Is that what you got?
I used 4 inches for my line.
Yeah, you got to be careful. You can't just use 4 inches or 2 inches. You can't use the height of the section. You have to use the location from the neutral axis. All right. And then for the copper, it's 10 kip feet times 12 inches per foot. And then this is just going to be 6 inches minus 3.08 inches divided by CU IX for the copper, which is 67.87 inches to the fourth. .16 KSI. Make sense to everyone? All right. I'm going to give you guys one more really quick problem. You guys should be able to do this in like 5 minutes. All right? Because I still have you guys for 4 minutes. Find me the maximum shear stress. Which, if you guys recall, is using the VQ over IB equation. Yeah.
Do we have to know the material of the?
Nope. No, I'm not asking you guys to do a design check. I am just simply asking you guys find the maximum shear stress.
What is the bottom feature you said? I what?
IB.
I.
Yeah, I is the second moment area of inertia, which for a rectangular shape, pretty straightforward. The only trick with this problem is really knowing what Q is. And once you do that, we basically covered every single type of problem that you can expect on the exam. And honestly, I think your exam is easier.
The last one? Or the next?
Than this, that was it. As for the, if it's easier than the last exam, I guess that's kind of like more of a subjective question or answer, because like, you know, some people probably like the beams a lot better. I know students liked the composites for the axial loading last time, but they don't probably like composites this time, right? They don't like composites for beams probably.
The composites is easiest.
You think the composites is easiest?
I think it is too.
Really? Wow. That's
It's
shocking.
more like a memory.
That's good, because I put a really hard composite problem on your exam. Not hard, a fun composite problem on your exam. can use it for the exam. Yeah, because some of the problems on there, like, you know, I'm not gonna ask you guys to draw the shear force moment diagrams because they're so simple. There's one question I ask you guys draw shear force and moment diagrams for, but everything else you should be able to either use the tables or they're not even related to the design table. So, but yeah, you can use it. Everyone get a stress? All right, since it's getting late, I want to know where everyone got with this problem. Did everyone find Q? Or was that the problem? Everyone found Q? All right. Let's just do it real quick. I is BH cubed divided by 12. What did we get for this? 72 inches to the fourth. Is that what everyone else got? Good. What is B going to be? It's the width at the point of interest, right? What is it?
So is it 4 inches?
All right. Now, what is Q?
Isn't that A? I don't know what this symbol is.
A tilde, Y tilde. But what is this?
Is it just area?
Not quite. Once you figure out the neutral axis, A tilde, Y tilde for the maximum shear stress is just the area above the neutral axis and the perpendicular distance of the centroid. So that's A tilde, that's Y tilde. So, say that again?
12 times 1.5.
Not 12 times. It's going to be the height of this total thing is 3 inches. Oh, wait, yeah. I guess you're right. Well, not 4.5?
1.5.
1.5, yeah. So if that's 3, that's 4 inches. That means your area is just the 3 inches times the 4 inches times this y bar here, which is equal to 1.5 inches. So that's what? 12 times 1.5. What is that? 16? 18? 18 inches cubed. And so tau max is equal to 1,000 pounds times 18 inches cubed divided by 72 inches to the fourth times 4 inches. And what did you get? 62.5 psi. Yes?
B is just the width of that.
It's the width at the point of interest of any material that's there. So you'll notice on the previous homework assignment, if you had 2 legs, it was the combined thicknesses at the location. And also another note that I did tell you guys last class is you could have just used that for a rectangular shape. And you will have found the same answer. But if I give you another shape, you'll probably have to derive some other expression. All right? Good luck on your exam on Thursday. And please don't miss the exam because I don't want to have to do reading of it.
Actually, I forgot to tell you.
Going on another cruise?
Yes.